Welcome to the first video of Math 350. In this video, we're going to look at some of the introductory concepts that you're going to want to know for the first day or two of class. We're going to list some important sets of numbers that are going to be important examples for the material that we're looking at. We're going to explore some fundamental properties of different number sets. We're going to introduce a model for rings, and rings are the fundamental concept that we're going to be studying this semester. And then we're going to give an example of some issues surrounding the concept of closure. And finally, a word about my buddy Peeves. So here are some number sets you're probably familiar with. I just want to make sure that you also know the notation that goes along with them. So the first one is a funny looking n. That's for the set of natural numbers. And these are also called the counting numbers, and for our purposes, those are all going to be all the numbers 1, 2, 3, 4, etc. Some definitions of the natural numbers include 0, and that's perfectly fine, but just for the purposes of our class, we're not going to include 0 as a natural number. However, we do include 0 in this next set, W, that is the set of whole numbers, and that's just the natural numbers along with 0. Next is Z, which stands for the set of integers, and that's all the whole numbers plus their additive inverses, which is a fancy way of saying the negative numbers. The negatives of the whole numbers. Bad, Darren. Q represents the set of rational numbers, and those are going to be all fractions m over n, where m and n are both integers, and of course we can't have 0 in our denominator, so n is not equal to 0. R represents the set of real numbers, and to define that properly, that's going to be very difficult. But it does include all rational and irrational numbers. That's not much more helpful, not much more precise. It's difficult for me to define precisely in a short way on this video. But if you're really interested, you can take Math 408, and we'll spend the first half of the semester getting to the definition of real numbers. Yeah, I'm not joking. C represents the complex numbers. Those include the square root of -1, which we denote by I, and all numbers of the form a plus bi, where a and b are real numbers. So our number sets have some really important properties that we're actually going to explore a little bit in our first day of class. They have some arithmetic issues that they have, and what I mean by arithmetic, that's just all the regular arithmetic operations that you do on number sets, right? So you can do arithmetic on all number sets, and of course there are going to be some restrictions. You can't just do arithmetic on any two numbers that you want to. That includes addition, that doesn't have any restrictions. Subtraction sometimes has restrictions. Multiplication almost never has restrictions, but division also has some restrictions in some of the sets that we deal with. We also have the concept of order. In other words, we can put the numbers in order, right? Well, except for the complex numbers, right? But other than that, all the other sets that I mentioned in the previous slide, we can put those in order, which means that if I take two random numbers A and B, I can tell you which one comes before the next one, if I actually tell you what the numbers are. So you're either going to have A comes at or before B, or, right, or B comes at or before A. That's the less than or equal to sign. One of those two things has to be true on any numbers, again, except for the complex numbers, which are kind of weird. One of the big questions we're going to be asking for the first, half to maybe 2/3 of the semester is, what is a ring? Okay, and I could just give you a definition, but it's going to be much more helpful when we go through some examples and sort of see the issues that are involved. But for now, all we're going to have is a model to tell us what a ring is. And our model is going to be the integers. So a ring is something that has addition and multiplication, and has properties that are similar to those of the integers. And that's a little bit vague, but for right now, that's what we got to work with. So note that we don't have to worry about putting them in order, because it's going to happen that we don't want to require a ring to have an order. And we'll see in some of the examples why that's going to be the case. All right, so another concept that I want you to be familiar with is something that is called closure. And we say that a number set A is closed under an operation. So a number set could be the integers, could be the natural numbers, could be the complex numbers. And we say that set, it's important that we're talking about the whole set is closed under an operation if doing the operation on elements of the set results in a number that is also in that set. So that's kind of a mouthful. Let's look at some examples to see what some of the issues are. So if we look at the natural numbers, for instance, for addition, right? If I add two natural numbers, any two natural numbers, the result is going to be another natural number. And what that tells us is that the set of natural numbers is closed under addition. However, subtraction is another issue, right? If I subtract two natural numbers, sometimes I get another rational number, like 5 minus 3 is 2. But sometimes I don't. If I subtract a larger number from a smaller number, like 2 minus 5, that gives me negative 3, which is not a natural number. So the natural numbers are not closed under subtraction. For multiplication, multiplying any two natural numbers results in another natural number, which means that natural numbers are closed under multiplication. But division, again, if you're not careful about what you're dividing, sometimes you get another natural number, but if you divide one natural number by another one that is not divisible into that first natural number, like 7 divided by 4, it's not a natural number, so it's not closed under division. All right, so moving on to my favorite model, my favorite way of thinking of things. This has to do with how we approach our proofs. So I call the model Peeves. If you want to hear where that comes from, you can ask me sometime. But I think of Peeves as someone who makes it really difficult to make you prove something. Now, of course, someone can make you difficult to prove something by like bonking you in the head or something like that. That's not what I'm talking about. What I mean is Peeves is bound by the rules of logic, but otherwise can be as disruptive as possible as you are writing your proof. So Peeves basically looks for bugs in your proof. Peeves is annoying, but actually in many ways very helpful, right? Peeves helps us keep our proofs logically sound. Peeves tells you the unpleasant things you may not want to know, but that you need to know. Points out errors in your proof, right? Things like hypothetical cases that you have not addressed yet, or possible counterexamples that you have not eliminated. And the most important thing is Peeves can't just be annoying to be annoying. It's got to be bound by logic. It has to be some sort of logical issue. But other than that, perfectly free to be extremely annoying. Not mean, though. Playful, maybe a little teasing, but not mean-spirited. Thing to remember is that making errors does not make you a bad mathematician. If so, I'm one of the worst, right? And even embarrassing errors don't make you a bad mathematician as long as you learn from them and end up with a product that is legitimate. All right, so now what I'd like you to do is try coming up with some arithmetic and order properties for integers that were not mentioned in this video and see how many you can come up with. And once you do that, you can feel free to move on to the next video. That is arithmetic axioms related to the arithmetic operations.